Hello guys, thanks for coming to our OLED Wave paper reading channel. Today, we're gonna be reading a classic paper. Its title is Seed-TTS, a family of high-quality versatile speech generation models. We have been reading a few TTS paper before, and if you like our channel, please don't forget to hit subscribe and turn on the bell. All right. This paper, it's an archive paper. I don't think it's published. It's written by a C team at ByteDance, or AKA the mother company of TikTok. What's their contribution? Well, it's first of all, they are saying that they offer the superior controllability over various sorry here, or various speech attributes such as emotion. I'm fairly excited about their work on emotional TTS. And also, they propose a self-distillation method. This is also new for speech factorization. And also, they also present a non-autoaggressive variant of TTS called Seed-TTS DIT. Well, they use something, or they utilize a full diffusion-based architecture. I wouldn't say all the threes are completely new, but I would say that according to what I've seen so far, the Seed team is the team that can best utilize these technologies. This is why this paper is more like a technical report. Even though they're not fully disclose their algorithms in their paper, but we can still benefit from the writings they have, or the details, or the information they share in this technical report. All right. Well, demos, right? I believe that all of you have listened to the demos because this paper was published almost a year ago. Introduction. Well, I like to go through the introduction line by line because the paper did not describe too much about their algorithm, or they didn't mention anything about too much about their algorithm. But in the introduction, they do try to give our readers a sense of direction. Why they pick up this, or why you shouldn't try something else. Okay. This is okay. Why do you want to build the Seed-TTS? They want to build a speech generation model that approaches human level speech. This is a very ambitious goal. I wouldn't say they have achieved that, but they have made a significant progress in this. In this paper, in this technical report, they mainly talk about three things. First is zero-shot speech in context learning, or AKA ZSICL. Second thing is a speaker fine-tuning. Third thing is emotion control. For the first thing, zero-shot speech in context learning, it means if you have read our, listened to our paper reading about Vali, it's about using 3 seconds of speech of a certain person. How can you synthesize or convert another person's voice into this person's voice? Right? Right? Is it right? Or okay, let me start from beginning. Given a registered voice of 3 seconds, of 10 seconds, or even 15 seconds, then given a sequence of text, now I want you to generate a speech of this person. And because this is autoaggressive model, sometimes most of them is an autoaggressive model, they can keep generating the speech if you feed more text or speech into it. Okay, just feed text into it. The second thing is called speaker fine-tuning. Have you listened to some deepfake audio? It's about how to synthesize some celebrity's voice. But this speaker fine-tuning, you have access to more training data, for instance, 10 hours, even 20 hours of labeled data. I mean, speech with text. The third thing is called emotion control. That's, it's very obvious. You can say, ask the TTS to generate happy voice, sad voice, and etc. They introduced two novel techniques. Well, I can see the authors are keeping repeating the things they mentioned. You just have to pay attention to this. Speaker factorization and the preference bias through reinforcement learning. Factorization through self-distillation and the preference bias through RL, okay? I do recommend if you want to work on this in this domain, make sure you read the reference paper they mentioned here. They're very good, I would say. I skimmed some of them. Don't forget the word simple. What? If you write a paper, if you're a PhD student, if you write a paper, never write simple in your paper, okay? Because most time it's not simple, and writing it simple is making your paper look okay. To this end, they design a non-autoregressive NAR variant of TTS. So it might be confusing because the paper has two structures. I will cover in the following slides. They first use something that's everybody using, autoregressive variant of Seed-TTS model. Then they tried a non-autoregressive model. They're repeating themselves again. Key contributions. All right. Regarding their method, first of all, what's their autoregressive method? Yeah, of course, they have another method called a non-autoregressive method. Well, here in figure 1, they discuss about their autoregressive model. It seems very obvious to you, okay? First of all, you start off with something like a Valley model, right? This is Valley again. If you have not read the paper and you don't want to read the paper, you can check the Valley keyword in our channel. You can find the paper, okay? The point is, first you get a speech, then you send it through a speech tokenizer. I prefer not to call that tokenizer because you're getting embeddings or not tokens. Or you you actually get embeddings, then you discretize them, right? Then you get tokens. It's not the tokenizer you use for text tokenizer, okay? Actually, this is a speech encoder. You have to train that encoder with lots of data. So my understanding is that if this is a tokenizer, you don't have to train it, okay? Then you get speech tokens. Then you get text tokens. Okay, this is very easy to understand. They forgot to draw something like this. Text tokenizer, okay? Then you have text input. Remember in the Valley model, it's all about given the input speech X and given the speech reference speech C tilde and given the text X, what's the next output token? speech, because the speech token, okay, what I would call it encoded speech or something. What's the next output of your encoded speech token, something like this. You can see, I don't want to go through the value again. This is what it's about. This autoregressive transformer, this is all about getting the C. And this is autoregressive. Once you get the C output, then it's indeed being fed back into the input, okay? Then it's keeping moving the data forward and keeping getting the speech generated from it, okay? But have you seen the issue here? Well, the C is the codes, or the code in the code book. It's discretized. It's not a continuous signal. And they mention that their acoustic vocoder needs, you see, the acoustic encoder is separately trained with a design similar to this paper. This paper, what is this? This is a GAN-based vocoder, okay? You can check this paper on page 14. They mention about their RVQ GAN. Vector quantization, residual vector quantization GAN, okay? And then they need something like a Mel scale spectrogram, which is a continuous signal as the input of the vocoder, but this is a discretized. You see this? You see the discordance here. But this is why they need this some module in the middle. They use a diffusion transformer. You can definitely try something else for sure, but according to them, diffusion transformer works really well. This is to convert or transform or transduce the discretized tokens into continuous signal. Okay. Discrete signal. This is continuous. Okay. But how they do this? They did not mention in their paper. And I plan to find the papers published by ByteDance and record another paper reading for you. So please hit subscribe and don't forget that. And then I will get updates on the paper I found for you. Okay. And they also mentioned that they're keeping mentioning this. They train a large amount of data, orders of magnitude larger than the previous large TTS system. Okay, guess how many data was using in the Valley paper? It's 60,000 hours. And if you're saying that orders of magnitude, that means I think it's not just one magnitude larger, okay? So I can rule out 600K hours. So it's at least 2 magnitudes larger, right? Otherwise, they won't use a plural form. So this is my speculation. They use at least 6 million hours of data to train their speech tokenizer plus their autoregressive transformer, which is their body model. So you can see, okay, a much larger valley with more than 6 million hours of data. Probably 60 million hours. You don't know, okay? And what else? Okay. Yeah, and they also mentioned that similar to the text-based language models, they also have the pre-training, fine-tuning, and the post-training. I would say the pre-training is like training the value. You have to train the encoder unsupervisedly. Fine-tuning, I think they usually talk about the how do you train their diffusion transformer. And post-training means they have some instructions, or they have some reinforcement learning procedure. So this is my speculation. They didn't mention that whether they train, how they train this model. Okay, my speculation is they first start off with training this section. That's the first stage. So after this, because this can be done unsupervisedly, right? And then they put a diffusion transformer and acoustic. Oh, yeah, they also trained this acoustic vocoder. This is step 1, the 1.1. This is step 1.2. And then they train the whole system. Or they start to fine tune this, or they start to reinforcement learning this. This is step 2. This is my speculation, because they mentioned that their acoustic vocoder is separately trained, and they do use the value model. No, they are repeating themselves again by mentioning what they have observed. I just highlighted for you. I don't want to read them again. This is the first one. Okay. They reduce the stability issue. Well, this is very vague to me, because they have not quite defined what the stability is in TTS system. But this technical report, and they mention many vague concepts. You can, it's on your own. You can try to find the related works. Okay. Yeah, there's no algorithm, right? So let's directly jump to their experimental section to see how it works. The first is the zero-shot in context learning, or they are keep using the ICL. I think this is the word they created, so I'm not very used to it. But this is ICL means in context learning, or the body style generation. Okay, they created objective set and subjective set. I think they have released a subjective set for other people to use. Kudos to that. The objective set is derived from public corpora. So this has issue of training data contamination. Just Google the word or ChatGPT the word if you don't know what this means. Contamination. They're using public data for training their data. The settings are standard, and then we look at the first table they talk about. SIM means the similarity to the target speaker, and then you can see this is for English, this is for Chinese. It's interesting that on the objective data set for English, the human speech works the best, but on the Chinese data, their TTS or Seed-TTS works the best for WER. But for sim, it makes sense. Or it doesn't make sense. Makes sense? Because they said their similarity is better than the human being's voice to the actual target speaker. It's target speaker's voice, but then they create something that's more similar to the target speaker. But let me tell you, the way they done this similarity calculation is by using a wave atom. I think I read the paper wave atom, or if I have not, I might have read a paper called a wave to vec. Just search that. Wave to vec 2.0 or Hubert, similar things. Just search the video in my channel. You will find them. I have a paper reading on them too. It's fine-tuned on speaker verification test. So this is not human being evaluation. This is just computing the causality similarity score between the speaker target speaker embedding and your generated speaker embedding. Okay. So I personally think this is problematic. They have to look into this. And that it's very interesting result. And they're saying that their generated voice on the subjective data set is better than a human being's voice regarding comparative mean opinion score. That means human being will, this is subjective score. That means human being would rate their speech with higher mean opinion score compared to the real target speech. This is also mind-boggling to me, because the theoretical upper bound of your speech synthesis is 0. You cannot go negative. So I'm really curious, how do people evaluate these CMMOS? Because I do have listened to their results or demos, the output of their demo. Their voice is like very high quality. So I'm wondering, if you listen to a studio quality speech of synthesized target speaker's speech versus a real target speaker speech recorded in a normal environment, the sound quality, I didn't mean the naturalness of speech, is worse than the synthesized speech, right? And then it might be possible for human beings to give lower score to the original target speaker's voice. So this is the issue of their setting of testing, okay? And then they talk about their in-context learning. Yeah, they're really proud of their scores. So they're mentioning the numbers in the table again, and they're mentioning that all the previous works before this one, they produce something like CMOS result below -1. That means they're behind, at least 1 point behind the human being. I think CMOS range from 1 to 5. Okay, and that, for example, suppose human beings like 4 point, you give human voice 4.4. Other ones, I think. Oh, that's not what I meant. That's not what I meant. They compared their generative voice with other techniques, not with human being. So they're saying that they at least have a -1 difference compared to other ones. Okay. Oh, I was wrong. Due to copyright restriction, they're not releasing the subjective test set. I think it means the test set. Okay, I thought they released a test set. I was wrong. I mean, they're your test set. Why can't you release them? Okay. But each speaker, Okay. Okay, they are conducting a unfair comparison. They're comparing the traditional speaker fine-tuned TTS model. You know, in the zero-shot TTS model, zero-shot in ICL, you have 15 seconds of audio and you generate the voice, right? Like they shown here. That's their setting. And then in the traditional speaker fine-tuning, you have roughly, they're using 5 hours of data to fine-tune the TTS model. Of course, they have transcription, a well-trained traditional TTS system. And they're seeing that they create some easy speaker or common speaker. I would call easy speaker because they also mentioned hot speaker, okay? Just to see how this thing works. And they say that for easy speaker, they demonstrate they're doing better, okay? See? But easy speaker, they got win. But for hot speaker, the fine-tuned TTS model win. Of course, they have used the 5-hour speech other than 15 seconds of audio, and they do this well-trained or fine-tuned separate system. They're supposed to be, I mean, intuitively should be better, right? And they're mentioning that they speculate because for hot speaker, they speculate that it's because the accent and unique speaking style are not preserved faithfully. And also everybody may raise this question, and they raise themselves, saying that what if they include something longer prompt? For example, is it possible for them to include a 5-hour prompt? Because, you know, nowadays text language model can take in super long prompt or super long context. But I mean, of course, I know 5 hours is long as a context, but can you take it? You know, this is a question. I believe they might be working on this right now. And also, they talk about speaker understanding evaluation. But this is very, I think they want to talk about the speaker understanding, but actually they're just doing ASR. ASR is one part of the speaker understanding. It does go from speech to text, but not go from text to summarization or understanding results. They synthesized LibreSpeech data by just looking at LibreSpeech text. And then they use the synthesized speech to train a model. And then the model is then being used to evaluate the ASR performance on the test set of LibreSpeech. Of course, the synthetic data is getting worse results. I think this is not new because, you know, TTS data has less amount of noise and or less variations. They're not covering enough amount of data, so LibreSpeech result became worse. But it'll be also interesting to see that if they test on using the model synthesized from LibreSpeech and test on other domains, right? For example, switchboard, or I mean, even if you're doing the maybe common voice, yeah. Visualizing speaker similarity, I mean, if you like C drawing, that's up to you, but I'm really not into the TSCE stuff because it's not a quantitative study. It's just to give you a visualization of how it works. And this is section 3.2, their second part, speaker fine-tuning of their algorithm. Of course, there's no algorithm. It's very straightforward, right? It's still this model, but they already have, you can see in this one, all you have to do is yes, I think they roughly mentioned about what they do. They perform SFT on top of the base TTS pre-trained model. Okay. Of course, this time they get more data and they're supposed to get better results, right? Okay. And they also for this one, I think this is what I think. The model architecture is slightly different than this one because they do not need a diffusion transformer. This is my personal opinion. Maybe they do. Oh, I was wrong. They do still need a diffusion transformer because they do need to go from the discrete signal to continuous signal because the acoustic recorder only takes continuous signal. But this time, what they just not have just one reference signal. They have many reference signal because they have a training set of about 5 hours, so they can keep feeding the pairs of speech and the text and the target speech into the system. Am I right? Or you can correct me if I were wrong. I think in this fine-tuning stage, they do not need this speech tokenizer, right? Because all you have to feed in is the text and the target speaker voice you want to generate. So you should not need this for your speaker fine-tuning because you have the data now. Okay, I think we solved that model architecture problem and also data controllability through instruction fine-tuning. Yeah, I think still in the instruction fine-tuning, if they have hours of data, you don't need this speech tokenizer at all. But if you do, yeah, you don't need the speech tokenizer. But the difference is you put something more in the text besides the content of the speech. But you can have two things in it. The first thing is the content of the speech, what you want the TTS to synthesize. The second is the emotional label, okay, into the text. Then you start this fine-tuning procedure. It's let me check whether they use the emotional speech or emotional text. Yes, I think they use the text as the emotional label. Okay, you see, they have a speech emotion recognition model to tag their speech. Okay, I think right. Well, this also I would say this evaluation is done in a rush. I would say they use a emotional recognizer to recognize the emotion of generated voice, which I think you should at least include another human evaluation results, right? Okay. I might have issues. The paper, I would say that they didn't quite mention how they train their so-called controllability versus instruction fine-tuning. I think they do what I said. They have to have voice actors come into their studio and give them prompts to ask them to act in different emotional ways of speaking the prompts. And then once they get them, they're using this model architecture to train that, except that there's no speech tokenizer. The training input would be the text with emotion, and the output, you're supposed to output a emotional speech. Okay, that's how they train that. But they do benefit from a pre-trained model, because all you have to do is probably, you don't have to tune this autoregressive transformer too much. All you have to do is to tune this diffusion transformer. Try to go from discrete signal to continuous signal, and finish the speaking style transfer. This is fantastic. Okay. I think I explained how they do these two things. And low latency and inference, I'm thinking there's some keywords you can just search by yourself. They're not new at all. Causal diffusion architecture, not new at all. And also they use a consistency distillation. This is about the perturbing your training sample, try to make the model to output the similar embeddings or tokens as before. And the modified flow matching algorithm. This is very interesting. This paper I read it, but they talk about modified flow matching algorithm. I'm gonna search what paper these ByteDance people publish and try to read that paper. Please keep tuned. I will read that paper. Yeah, streaming processing, and you can see that the latency, they have a huge job, because that's offline model. This is not offline model, right? This has a huge improvement, and by including many different sort of flash attention acceleration methods here mentioned here, I think model quantization, they reduce the RTF by about 80% or 90%, about 90%, which is huge. And they didn't see much degradation in the CMOS. Okay. Model extension, speech factorization versus distillation. What is speaker factorization? It means you want to decompose the speech into various attributes, including what I think is so in the past, usually people feature engineer these attributes. Or they use precise network architecture tuning, okay? But they're saying that they're not preferring these methods, so they propose something called a self-distillation. I believe this is new, but so I'm trying to read this paper, or find this paper, or this paper related to this, and read it to you. This is by ByteDance, for sure. This is new. The core principle, it means is to create controlled speech pair that share most information, yet different in one of few specific target attribute. This is very difficult, let me tell you, because they want to say, okay, this is a male voice, and I want everything to be the same, except I want to convert this to a female voice. How they do this? They probably use their own model, because their own model, you can feed in instructions to generate these, right? But the problem is whether this these what I mentioned can have the same feature they talk about. This is very important. Differ in one or few specific target attributes. So when you change the pitch or pitch changing the from male voice to female voice, does it only change pitch or it change something else? Because this is a neural network model. It's hard to control. But if you're using signal processing based method, your generated speech pair won't be natural, right? So it's a question for how to generate these data pairs, okay? Or how do they generate these data pairs, okay? And they're saying straightforward. I don't think it's very straightforward. Zero shot generation. Yeah, they're using the method I'm talking about, right? They feed a text and they say, yeah, they just generate speech, right? This is a text to generate, and they have a male registered voice and generate the female voice. Okay. Yeah, and then they can use how to generate pair. My understanding is that to get this pair, you have the male voice and female voice, right? You just use male voice plus text using their zero shot ICL. You generate the male voice, right? And then they also use a female speech voice plus text also through their zero shot ICL to get female voice. Make sense? Yeah. And then they got a pair of them. And they're saying that, okay, in this generation, I only changed the registered voice from female to male to female. And the generated speech pair should differ only in one of few specific attribute, aka the gender. But is that so? But I mean, how do they verify that? You know, that's a question for me. And then, okay, this is how they do it. They obtain the synthetic speech with the same content and prosodic pattern. Yeah, they introduce speaker perturbation into the diffusion module. The detail is not known. Details are not known. So I think this is crucial. Very important. They generate the synthetic speech with same content and prosodic pattern, but shifted timbre. Okay, you can ChatGPT these keywords: prosodic versus timbre. Okay, ask GPT to explain it for you. I don't have time. Basically, you can think about timbre is something that you can use for distinguish speakers from each other. Or prosodic features, they can have right over here. Okay, you can have pitch, loudness, the duration, intonation. In Chinese, you know, you have it's a tonal language. You have intonation here. Mandarin, and also stress. English word, it can have aboard or about. Yeah, stress, different syllables or in different parts of the word. And you can see these things has nothing to do with speaker characteristic, right? Or it does. It's not completely decorrelated, right? Because different speakers have different pitch, right? It's in the prosody. But this is what this author meant, I think. And then yeah, this is what they talk about. And then it's very important for them to share the same content and prosody but different timbre. I doubt that. Okay, because they have not approved it, because they have not approved this. The network must disregard the timbre embedding in the token sequence. If they successfully generate these pairs that share the same content and prosody but different timbre, the model is supposed to be doing this. Okay, and this is their architecture. Okay. Is this figure 4 or let me see? Well, yeah, this is a diagram of their proposed voice conversion. Yeah, because they do this in the voice conversion. So this is not zero-shot ICL. This is a voice conversion. It does not have text, or you don't have to have text. This is how the deepfakes stuff is about. Okay, you have speaker's voice as input and another speaker's voice as a registered voice, right? This thing can have 3 seconds, 10 seconds, or 15 seconds. But this thing can be arbitrarily long. They can be 30 seconds or maybe 5 minutes. It's up to you. And because the diffusion transformer, I'm wrong. I might have to cut the speech or not. Can you do 5 minutes? Oh, I think they use causal diffusion, right? So the diffusion transformer is a streaming. It's a streaming diffusion transformer. So you can have 5 minutes of speech. So just keep feeding speech input, okay? And then you got the synthesized speaker B's voice, either 30 seconds or 5 minutes. Clear? Yeah. The method is not yeah, you see this not, they have mentioned that. Okay, the next is 4.2 preference biasing through reinforcement learning. This is slightly new, I would say, because I can see that they are using, wait a second, why are they talking about this self-distillation again? Is table 6 related to, they're putting table 6? Oh, I think because table 6 is still belongs to 4.1. Yeah. Their self-distillation approach in the voice cloning task, or no, sorry, voice conversion, not voice cloning, voice conversion task is significantly better in terms of WR and SIM, but they do not have the CMOS score. I believe this is so significant, the CMOS score should be better. And also, I think I attribute this to the possibility of they feed in many pairs of data into this zero-shot conversion stuff. Yeah, you see, because they have these fantastic, let me go to here, this fantastic architecture for generating pairs of speech with only a few attributes to be ordered, to be changed. So they can use these pairs of data, probably as many as they want, in this voice cloning task by training this model, okay? Just to make this diffusion transformer better and better. That's their why I think this is why they have way much better WER and the same similarity measure compared to the previously published work. Okay. Talking about the reinforcement learning, I'm not sure whether you have read Rohit, the researcher from Google's paper. He used because I'm an ASR person. He used the minimum word error rate in end-to-end this ASR training, and indeed, minimum word error rate is actually a how to say that? There's a reward function for minimizing the WER. So it's indeed already RL. Okay, this is RL, minimum word error rate, and that they're doing the similar thing by minimizing the word error rates of the generated speech, and also minimizing the maximizing the similarity score. So they put it into the award function. See, of course they get better performance, because there's a reward on that. But whether the CMOS is better, CMOS is better. I believe that you cannot over RL on this case. Otherwise, like they mentioned that they observed a funny effect, which is the reward hacking. The model tends to generate slower and more clearly pronounced utterance. Yeah, just like I speak very slow and clearly for you, so you would like to subscribe my channel, right? It's called also reward hacking, maybe. So this is not supposed to be happening, but this is also that's the tricky part, carefully network tuning. Okay, how to do that, So I believe that they need to develop a better reinforcement learning reward or award functions besides the WER and the similarity measure. Okay. Yeah. Also, they talk about speech emotion recognition error. It's much better. It's not surprised. And this is new. And I will find the paper and try to find their published paper and see whether I can read it to you. They train a full diffusion model. You can see in this architecture, they go from speech directly to diffusion transformer. There's no speech tokenizer and the autoregressive transformer. Okay, or aka there's no neural language model encoder or codec. I think they call it, sometimes you can search the keyword called a neural language model, neural language codec, something like this. NLC, that's another keyword. So they directly go from speech into the diffusion transformer, and this is a non-autoregressive. So I guess you cannot take the speech that's too long into it, okay? Because this is diffusion, like image, it's not streaming, right? It's not autoregressive, is it? Yeah, this is. I think I read it before. Correct me if I'm wrong. What depends on the Yeah, the difference is that in the past, they try to estimate this. In their NFC or the pre-trained model, they try to estimate the speech codes by taking in speech, register voice, and text, right? And now they're just doing this. Go directly from speech what's the speech given the noise, right? Of course, they also put the text there. I think this is the text. I would say this is the speech to be modified. Okay, that's their model. The speech to be modified, and this is a text, and this is a speech modified. Okay, you can see how to go this from to this. I think this is a procedure of Gaussianize the speech into Gaussian noise. And then they skipped this, I think. They didn't draw that, but there should be something here, okay? I'm just telling you the general architecture of their model, what it's supposed to be. And then once you get this, they mask out certain words, or they mask out the certain duration in the speech, and then they put a text and the highlight. Okay, the dog word is what I wanna use to replace the original masked out word cat, and then the diffusion transformer is supposed to generate or fill in only the cat speech for you, okay, or cat spectrogram for you, and then they use acoustic vocoder to generate everything. Of course, this thing is tuned end to end from here to here, okay. And interestingly, their full transformer, full diffusion model works much better than ICL, which is very impressive, especially in the. But the task is not 0 ICL again. I think, is it? Well, this is not exactly like the task shown before. That task before was given a long text, and you have a 15 seconds audio go from this speaker to another speaker. Oh no, generate the speaker's voice given the text. But this one is a context editing or changing the speaking rate. You only have to modify a certain part of the speech. Okay, the speech is given. So the speech can be 30 seconds long. And the text is short this time, I think. The text is just correspond to the speech. Okay. Task is slightly different. There's some analysis I will skip. This is a model application and limitation part. I will stop here. Really appreciate that you are having the patience to listening to me discuss or sharing this paper with you. If you have any comments or thoughts, please leave it in the comment section. And don't forget to hit subscribe. I will try to read the more details of Seed-TTS, ByteDance TTS to you next week. Thanks very much. Goodbye.